All right, in this video, we're going to finish the examples here in section 5-4, the sum and difference formulas. And we kind of start here with a doozy. Let's see what they're asking us to do. Write the cosine of quantity arctan 1 plus arc cos x as an algebraic expression. Well, what the heck is that? Let's see here. We got the cosine. Oop, that's supposed to be a C. We got the cosine of, it looks like, a sum. So let's call U, this piece, arctan 1, and then V, oops, that's supposed to be a V, the arc cos of X piece. So we're dealing with the cosine of a sum. We know what formula we're going to be using. We got to sort of dig into the U and the V. So I'm going to draw a couple triangles over here. Good enough. Those are supposed to be triangles. You get the idea. So here, U, I'll make that in red. U is this arctan 1. Well, we're dealing with the tan function. What two sides of the triangle are tangent? Opposite over adjacent. So from angle U, our value is 1 or 1 over 1. Opposite is 1, adjacent is 1. If we do the Pythagorean theorem, a squared plus b squared will be 1 squared plus 1 squared will equal c squared. So that'll add up to 2, and then we'll square root both sides. So our hypotenuse there is root 2. Now the other thing is the V angle, that is arc cos x, or arc cos x over 1. Cosine deals with adjacents over hypotenuse. So the adjacent will be 1, the adjacent will be x, the hypotenuse will be 1. Here is angle V. So Pythagorean theorem. This side over here, we'll just call it A. So a squared plus b squared is equal to c squared, or 1 squared. To get a by itself, we'll subtract x squared. A squared equals 1 minus x squared. That's squared. And then to get a, we will square root. So our missing side is radical 1 minus x squared. Do a little arrow there. Radical 1 minus x squared. That's a minus. There we go. All right. So let's expand this out. We have the cos of a sum formula. So this is going to be cos, cos minus sine. Cos minus sine. Now this is where the problem gets kind of interesting. The first thing we put in for angle U is arctan 1. So this is arctan 1. I should have made my parenthesis a little bit bigger. Next up is arc cos x. Arc cos x. And then after the minus sign, we do those same angles again. First it'll be arc tan 1, and then next up will be the arc cos x. Arc cos x. Kind of messy, but we'll work through it here. Okay, well, the first one here, arctan of 1. We could go to the unit circle, or I mean to the triangle we drew over here, but even think on the unit circle. Where arctan 1, what angle gives us a tangent value of 1? Positive 1, and remember to stay in the good quadrants. Arctan lives in quadrants 1 and 4. So the arctan of 1 is at pi over 4. That would be here in the first quadrant. So this, the red part in here, the arctan 1, is going to turn into pi over 4. So that's going to become the cos of pi over 4. Here, cos and arc cos, what do they do to each other? They cancel each other out, just like squares and square roots. They're inverse functions, so the cos and the arc cos cancel, leaving just here x. So we got a times, that's not going to let me do it, times x. Minus sine of arctan 1. Again, we could go to, well, let's go to the triangle and see how that works. So if we go to this triangle where we have our u, sine is opposite over hypotenuse. So that would be 1 over the root of 2. And we could simplify that to root 2 over 2. Well, that would give us the sine value. The sine of that would give us root 2 over 2. Or if we do it sort of the step we did over here, arctan of 1 is pi over 4. Here's where the triangle becomes absolutely necessary. The sine of the arc cos x. So we're going to go to the blue triangle here, our V triangle, and we need to find the sine value. Sine is opposite over hypotenuse, so that'll be our radical, 1 minus x squared, over 1. So I'm going to have to erase this, and we're just going to have to turn that into a times root 1 minus x squared. I guess that's close enough to a 2. Okay, now we can keep simplifying here. This cosine at pi over 4 is root 2 over 2. And we're going to multiply that by x, so I'm just going to put an x here in front of the radical, x times that root 2. And then minus, here sine at pi over 4 is also root 2 over 2. And we're going to multiply that by another radical over 1, or 1 minus x squared. So one last thing to sort of make this look a little prettier. We can give it a common denominator. Here we have a 2 minus 2, so our common denominator is 2. And then our numerator will have this term first, x times the root of 2, and then we will minus. Here we got one radical times another, so we could put them under one radical and distribute. So that'd be a root of 2 times 1, or excuse me, this is all under one big radical. 2 times 1 is 2, minus 2 hits the x squared, it'll become a minus 2x squared. So there's our final answer. We've written this trig expression as an algebraic. Notice where we started, a cos, we had an arctan and an arc cos. When we're all done, it's only numbers and x's. And that's just what we were looking for. Those same triangles that we set up here for arctan 1 and arc cos x for the u and the v, I believe you'll be using those exact same ones in the huddle problem. All right, this is a little easier than what we just saw. We're just going to verify a cofunction identity. On the left side here, we have cos of half pi minus x, and they're saying that's equal to sine. This is the cofunctions of complements are congruent. You might remember me saying that many times at the start of this section. So we have this cos of a difference is equal to sine x. Well, let's see how this is derived or verified. Well, we got the cos of a subtraction, cos of a difference. So the pattern will be cos, cos plus sine, sine. Cos, cos plus sine, sine. And we put in the angles. First is a half pi, and then an x, and then another half pi, then an x. And to the unit circle. The cosine at a half pi, that turns into a 0 times this cos x. Well, 0 times anything is 0, so that term will be gone. And then here, the sine at a half pi, that's positive 1 times sine x. So 0 times cos wipes this out. We have 1 times sine, and that's equal to sine, just like we were trying to verify in the identity. All right, here's the huddle problems to practice with. Remember, for this, you can use the same triangles as we set up in the example. So pause the video, try these out, and then verify your solutions. Okay, so in this one, we're doing the sine of a sum. So the sine of a sum formula will be sine cos plus cosine. Sine cos plus cos sine. And we're going to make the u arctan 1. So first over here we'll go arctan 1. And then the cos we'll have next the arc cos x. And then after the plus sign we have the same angles again, arctan 1. And then sine of the arc cos of x. Now let's do these purely off the triangles, because in the example we didn't exactly. Let's see here for the arctan 1, that'll be this top triangle. I'll sort of put a little red in there to go with this red part right here. The sine at that triangle. Well, sine is opposite over hypotenuse. Opposite is 1, hypotenuse is root 2, so this all will turn into a root 2 over 2 when we rationalize. Root 2 over 2. Or the way we sort of did it in the example, we did the arctan of 1. Well, that was an angle. Arctan of 1 was pi over 4. What is the sine at pi over 4? Root 2 over 2. Up next, we have the cos of the arc cos. The arc cos and cos will cancel, leaving just the x, so we're going to multiply that by x. And then we have our plus sign. The cos of the arctan, back up here to the red triangle, the cosine from angle U is adjacent over hypotenuse 1 over root 2, and again we will rationalize root 2 over 2. Now here we go to the second triangle, the V triangle. I'll put a little blue in there. We want to go to that triangle and find the sine at that value. Sine is opposite over hypotenuse, so that will be the radical over 1, or just times the radical, 1 minus x squared. Okay, now let me show you a different way you can do the final answer here. I saw this in the teacher's edition. Okay, what we would have done, just like in the example, here our common denominator is a 2 and a 2, so it's 2. And our numerator is a plus, so we're going to have a root 2 times x up here, or x times root 2. And then here, well, I'm going to leave this out for a second. In the example, we distributed, put it under one radical, radical 2 minus 2x squared. If I leave this undistributed, a root 2 times the radical, here's an alternate way to write this answer. Okay, the denominator is a 2. Could we write that as root 2 times something, sort of factor a root 2 out of there? Well, yeah, we could write it as the root of 2 times itself, the root of 2. Because if we multiply it, we would get back to 2 where we started. Now that we've written it like this, we could simplify. We could factor a root 2 out of the numerator, cancel it out of both numerator terms and out of the denominator. So another way to write this, an alternate way, would be x plus our radical, 1 minus x squared, all over the root of 2. Okay. And then we have the verify the identity. Here is the sine of x minus half pi. Should be the same as negative cosine. So we go to the sine of a difference formula. That will be sine cos minus cosine. And in goes the angles. First thing goes in as an x, and then a half pi, and then an x, and then a half pi. Sine of x is just sine x. We're going to multiply that by the cos at a half pi. Cos at a half pi is 0. So that term will get wiped out. Then here we have a cos x times sine at a half pi is positive 1. So here the sine of x times 0, that goes away, and we're left with a minus cos of x, just as we were supposed to. All right, example 6. I believe this is our last example. No, we got one more. Write each expression as only a function of theta. So let's see what we got here. The first one, cos of a difference, the cosine of a minus. That pattern will be cos cos plus sine sine. Cos cos plus sine sine. This is kind of like the verify the identity thing, but we don't know what the finish line is. We're going to finish it down to something simple over here. So first in goes our theta, and then a 3/2 pi, theta, 3/2 pi. Okay, cos of theta is just cos theta. Theta. The cosine at 3/2 pi, well, that's 0. So 0 times this is going to wipe it out. And then over here on the other side of the plus, sine of theta is just sine theta. The sine at 3/2 pi is negative 1. So that negative will sort of come over here, multiply by this positive, and become a minus sine of theta. And there we go. Part B. Ooh, we get to use the tangent formula. All right. Tangent of, tangent of a sum. So the tangent of a sum, the pattern there is going to be tan plus tan in the numerator, and the denominator is 1 minus those multiplied, tan times tan. And the angles drop in. First is a theta, and then a 3 pi. And down here, a theta and a 3 pi. Let's see up top, this tan of theta is just tan theta. We don't know what that is yet. Plus the tangent at 3 pi. Well, let's see, 3 pi. Here's 1 pi, 2 pi, 3 pi is over here, and the tangent value on the x-axis are 0. So that tan of 3 pi becomes 0. Downstairs we have 1 minus, well, tan of theta is just tan theta. We don't know what that is yet. But we're going to multiply that by this tan of 3 pi, which is 0. So 0 times this zeroes that term out. So what we're left with up top is just a tan theta. Downstairs, just a 1. Tan over 1 is just tangent. So the tan of theta plus 3 pi is the same thing as the tan of theta. And we proved it. All right, example 7 here. Ooh, now this is a biggie. We're solving a trig equation. We are in the restricted interval 0 to 2 pi. And let's look at this thing here. I'm going to use a little color coding to make this sort of stand out. First, find all the solutions of sine of a sum, and then plus the sine of a difference, a minus. So we're going to use the two different formulas, sine of a sum and sine of a difference, and we're adding those together. I think I'll use black ink for that in the middle to differentiate between them. So let's see what happens here. First up, sine of a sum, and that's in red. So the sine of a sum is, the pattern will be sine cos plus cos sine. Sine cos plus cos sine. That's close enough. And then here's our plus. And let's just do the pattern here for the sine of a difference. I'll switch over to blue ink. And this will be sine cos minus cos sine. Sine cos minus cos. Ooh, I should have left a little more room there. Cos sine. All right, and the angles now. For the first one in red, I'll leave my angles here in black ink. X is first, then quarter pi. X, quarter pi, X, quarter pi. Over here in the blue, the sign of the difference, it's X and quarter pi also. X and a quarter pi, X and a quarter pi. Now, I didn't have room here. I even ran out of the room for the stuff here in blue. This is equal to -1. So let's start simplifying. This cos at a quarter pi, well, that's root 2 over 2. Let's see. So that will be sine x times this is root 2 over 2 plus cos x times the sine at pi over 4. Sine at pi over 4 is also root 2 over 2, and we're going to multiply that by cos x. We can put all that up in the numerator. Plus, ooh, and I see I'm going to sort of run into this. There we go, and I guess I could have made that in red ink so it matched above. And now we go to add. The second stuff is in blue. Here, this cos x, or quarter pi, excuse me, is also root 2 over 2, and that's times the sine x. Root 2 over 2 times sine x. And then minus sine at pi over 4 is also root 2 over 2, and this is times cos x. And I still don't have enough room. That's equal to -1. So let's see what we can do here. We could put all this over a common denominator. Yeah, that might be the easiest way to go. We got here everything has a denominator 2. First up top above this 2 is I'm going to put my radicals in front of my trig functions. Root 2 sine x. So root 2 sine x. Here is a plus root 2 cos x. Plus root 2 cos x. And then here's the black ink, the plus in between. Plus. And then here we got a root 2 sine x. Root 2 sine x. And then a minus root 2 cos x. Minus root 2 cos x. And again, this is still equal to -1. I've almost got enough room to write that in there. Let's see what happens now. Here is a negative root 2 cos x and a positive root 2 cos x. Those will cancel each other out. So now we have a root 2 sine x and another root 2 sine x. When we collect those, how many of them do we got? Well, we got 2 of those root 2 sine x's. Remember, we're still all over 2 here, and this is equal to -1. I finally have room to write it all in. Okay, on the left side, first off, these 2's are going to cancel, since we're down to a single term up top. So now we have the root of 2 times sine x is equal to -1. And to get the trig function alone, we will divide by root 2. So here they cancel, and now we have the sine of x is equal to, I'm going to rationalize this. Don't lose the negative, but that will turn into a negative root 2 over 2 when we rationalize. Wow, all that work. And we are finally on, the unit circle. So remember, sine values are y values. Where on the unit circle are sine values equal to negative root 2 over 2? Well, that happens at x equals 5/4 pi. And also x equals 7/4 pi. That was a lot of work, but the answers are beautiful. They are well worth it. And let's see what the book has here for graphical solution. We could type that monstrosity into a TI-89. Be very careful of your grouping symbols. And what they did here, to set it equal to 0, they added the -1 to both sides. So now on the other side is a +1. And you can just type that right into the Y editor. And then you'll see a graph roll out like this from 0 to 2 pi. And you could use the intercept feature on the TI-89 to nail down those. Here they are as decimals. Of course, our radian measures are superior. So here's a practice problems for you. This up here, again, kind of like verifying the identities. These should boil down to a single trig function of theta. This other one down here, you're going to do the sign of the sum and difference formulas again and find your answers. Here you're equal to +1 on 0 to 2 pi. So for A, sine of a difference. Let's see here. Sine of a difference, our pattern there is sine cos minus cosine. So sine cos minus cosine. And we drop in the angles in order. 3/2 pi and then theta. And 3/2 pi and then again theta. And let's see here, the sine at 3/2 pi, well, that's a y value. You're at the bottom of the unit circle, so that's a -1. And we're going to multiply that by cos theta. And then here, cos at 3 pi over 2 is equal to 0. 0 times sine theta, that term gets wiped out. So we're left with -1 times cos. So that'll leave us negative cos x. Negative cos theta. All right, on that next one, we got tan of a difference. So the numerator will be tan of a difference, tan of the first minus tan of the second. Below that will be 1 minus their product, tan times tan. And first in goes the theta, and then the 4th pi, and downstairs the theta and the 4th pi. So let's see, tan of the 4th pi, well, that's just 1. So the numerator becomes a tan theta minus 1. This tan at a quarter pi will also turn into a 1, so that's times 1 times this. This will be 1 minus tan theta. So tan theta minus 1. Oops. Oh, I'm sorry, the formula. This is a minus, but downstairs this does change to a plus, so this should be a plus. So our numerator, tan theta minus 1 over our denominator, 1 plus tan theta. Because we're adding in the denominator, we could reverse that order, because it just is a little more aesthetically pleasing to see that tan minus 1 upstairs and tan plus 1 downstairs. And there we go. Now for the doozy. Here's our a bigger one. And again, we want to just find all the answers from 0 to 2 pi. So I'm going to use red here. Sine of a sum. Sine of a sum is going to be sine cos plus cos sine. And then we're going to have, I'll switch again to black ink, plus. And then the blue, the sign of the difference, I'll do down here. That will be sine cos minus cos sine. And in go the angles. X and pi over 2 first. X and pi over 2 for these red ones. Now the blue ones we switch. X and 3/2 pi. That is a 3/2 pi. X 3/2 pi. Okay, here the cos at pi over 2, cosine values are x values. You're on the y-axis, so that'll be a 0. So that'll be 0 times sine x. I'll just write a 0 there sort of as a placeholder. Plus cos x times sine at a half pi. Sine at a half pi is 1. 1 times cos x is cos x. Plus. Now we get into the blue ink. Cosine at 3/2 pi is also 0, so that becomes 0 times sine x, so that just becomes a 0. And then we got minus. This sine 3/2 pi is a negative 1. Negative 1 times a negative cos turns it to positive cos. Plus cos. That is an S. There we go. And this is equal to positive 1. So cos plus cos are 2 coses. And that's equal to 1. And then we're going to divide both sides by 2. So cos of x is equal to a half. It's time to find our unit circles. Where does cosine equal a half? 2 spots. Cosine values are x values, so we have one in quadrant 1. That's a 1/3 pi. And then we have one down in quadrant 4, 5/4 pi. Remember, we were restricted 0 to 2 pi, so there are the 2 answers that work. Even assignment to turn in 55, 58, or 56, 58, 62, 66, 72. Again, if you have trouble with the even ones, the odd ones that are associated are listed, and they are also on Calc View or Calc Chat.